Today I'm talking about towards smart and connected buildings in cities, intelligent building operation for efficient, resilient, and healthy buildings. So first, I will briefly introduce some motivations, and then talking about how we can use occupant central controls in buildings for intelligent building operations, and then I will briefly touch some opportunities. So why actually we want to study the buildings? The building energy use matters. So if you see in this pie chart, this shows like in the US, 45% of the source energy is consumed by buildings, including both commercial and the residential buildings. This number is very similar worldwide. And then more than 75% of electricity and 45% of the natural gas in the US consumed by the buildings. More importantly, those numbers actually are no change in time. This figure is kind of old. The numbers actually generated in 2012, but you still actually can see the point I'm trying to convey here is that in next 20 years, the energy consumption from both residential and commercial buildings is still going to be significant. So lots of the government agency and national labs, the industries have been working hard trying to improve energy efficiency in the buildings. But in reality, there's lots of the inefficient buildings. So here I'm showing just examples. So this example is from the Leadership in Energy and Environmental Design rating system. So XX is the proposed savings used in the simulation during the design stage. Y-axis is actual measured savings when the building is occupied. So for all those buildings, actually, they are basically saving more than expected. For those buildings, they're saving less than expected. For those buildings, they actually consumed more energy than the code baseline. So why actually there's a large difference? Because there's large because there's lots of things actually can contribute to this variability. At least quite a bit of the factors. But today I'm only actually going to emphasize one thing related to human. So uncertainty in operating environment and the loads and the human building interactions will cause some efficient operations. Occupant behavior also is a key factor influence the building energy consumption. So, to address that occupant behaviors issues for energy efficient buildings, so currently we're doing one project sponsored by Department of Energy, APA-E. So this project actually is more than the simulation, but today I'm only going to cover this simulation suite. The project actually covered the simulation and testing in the lab and also the field testing we're currently using the buildings on campus. So today I want to mainly actually talking about how we can actually to use the simulation suite to investigate different types of occupancy sensor for nationwide energy saving potential in real world retrofit scenarios. The goal is to demonstrate at least 30% energy savings of the HVAC, heating, ventilation, air conditioning energy usage from occupant central control. So what's the definition for OCC? So OCC is an indoor climate control approach whereby the occupancy, occupant behavior, and occupant comfort, health information are used in the sequence of operation. So in here, we're mainly actually talking about occupancy and the interactions. For instance, we're careful when actually occupant is in the building, when they arrive, when they leave, and how long they're going to stay in the building. And then based on that information, you can adjust the room temperature set point. Also, you can adjust the ventilation rate. Other things we care for is interactions between the human and the buildings. For instance, you can actually open the windows, open and close the blinds. You also actually can, as a human, as an occupant, you can adjust your thermostat at your home, in some office. So all those things, they're going to have the significant impact on energy efficiency, thermal comfort, and health indoor environment. So what makes a successful comprehensive nationwide simulation? As I mentioned, one of our goals is to construct this nationwide simulation suite to do the evaluation. So the first is the various weather climate condition. We're trying to cover all the climate zones in the US. The second is different types of building. These basically give you the ranks of the different type of buildings in terms of number of buildings and a total floor space and total works for the man shift. So in the end, we choose the 4 commercial buildings and 1 residential buildings. These include medium office, large office, large hotel, primary school, and single family home. And then also we want to consider the baseline using the different building code. So these shows currently actually those code compliance the requirement for commercial buildings in the different states. So in the US, most of states now following ASHRAE standard 90.1, which is the energy standard for buildings except low-rise residential building. And then we also want to consider different sensors. So there's occupancy presence sensor, which you can actually use the PIR or acoustic sensor to detect whether the occupant is in the building or not. And also there's other type of sensor is called occupant counting sensor. So for counting sensor, you can actually use them to help you understand exactly how many people in a given room. And so that's the methodology we are following. We first choose the 5 prototype building models with a great potential to adopt occupancy central control. Then we customize the ASHRAE standard 9.1, 2004 and 2016 code compliance models to represent 2 levels of the efficient design baseline model. And then we adopt OCC modeling strategy for create advanced models using the different sensing technology. And then we're applying it to 16 different climate zones. And then last step, we assigned building construction weight factors, basically trying to understand nationwide energy savings potential. So first, for commercial buildings, as I mentioned, we have the 4 different building types: medium office, large office, and primary school. We evaluate 3 different sensing scenarios. The first one, we don't consider any occupancy sensing in the building. The second one, we only consider occupancy presence sensor. The third one actually is occupant counting sensor. So the last 2 represent advanced case 1, advanced case 2. Also, we need to understand occupancy schedule. We are using Lawrence Berkeley Lab occupancy simulator for the office building, the schedule, and then for the other building type, we just using some assumptions as I mentioned on the slides. And then for the control strategy, again, this is just strictly follow ASHRAE standard 9.1 and this standard 60.1, which is for ventilation for the acceptable indoor thermal environment, and also for the advanced control guideline, guideline 36. So that's the simulation result from this nationwide simulation suite of office building. You can see actually it's the 3 bars. The first bar is baseline. The second bar is from advanced case, which we only use the occupancy presence sensor. The third bar is the case we're using the people counting sensor. The heat map basically shows the savings compared with the baseline 2004 case, 2016 case. That's a saving potential. So we can see actually there's quite a bit of savings due to this OCC. They mainly actually due to 3 aspects: reduced building load because you have temperature setback, reduce the zone minimal supply flow rate, and reduce the system minimal outdoor airflow rate. The occupancy counting sensor actually only bring marginal benefit compared with the presence sensor. This is why actually you see here, these 2 bars, the savings is very close. So in general, the new office building will have smaller HVAC savings ratio. So that's why you see here, you compare with if you actually using the new version of the standard, because new version most of the time they have the more energy efficient measured. Another observation from here is if you look at the large office building, the savings number is relatively small. This is because in large office building, there's a data center there. For the data center, we were not actually applying any temperature setback or ventilation setback, because that is not for the that room actually is not for the office. That room is mainly for the equipment, and then we have to maintain certain temperature all the time. Some result from residential case. So again, for the building energy models, we're applying the different scenarios, including you will have slab case, you have heated basement, unheated basement, and then we studied the case in the 40 different American cities. These include top 30 metropolitan statistics data by population, and also some actually represent cities for International Energy Conservation Code climate zones. So that total is 40 cities. And then for occupancy schedule, this schedule is directly taken from Building American occupancy schedule. And then we apply some sampling and k-means method to extract this schedule. For the temperature setback schedule, again, there's a baseline. That's most of the time people are doing right now. And then we designed 4 different advanced cases. For those advanced cases, you basically have different setback. So totally, there's 16,000 residential simulations conducted in this study. So here is those results from the 16,000 simulation. On x-axis, that's the 40 different American cities. Y-axis is just different scenarios, and so those different scenarios also has the comparison with different baseline. One is using the AECC code 2006, another one is using AECC code 2018. The check mark in here means that we have the case, we can achieve more than 30% savings. This X mark means that we only be able to achieve less than 15% savings. So from this large scale simulation, we can see a deep setback temperature could bring additional 5% to 10% savings compared with that setback theoretic. And also we can see even the deep setback was applied, the method can only, the method basically cannot actually help us to achieve the goals we set at the beginning of this project. So we want to actually achieve at least 30% of HVAC energy saving nationwide. But you can see only actually you applying those very environmentally friendly temperature setback is going to help you to achieve this 30% energy savings. So I also, in the end, want to briefly touch this kind of opportunity I see if we can actually apply some digital twins, the tools. That's the well-being in building environment. So as we see, people actually spend 90% of time inside the building. So the well-being is strongly actually depend on links between the building environment, the person, the cultural and the social factors that drive health, productivity, and comfort. And then if we can use actually digital twins, the tools, to help us to inform better design, construction, operation, and use. So currently we have actually ongoing project that's the International Network of Networks for Wellbeing for Building Environment. We're trying to explore how actually we can bring the people with different background and to promote the well-being building environment. As we see actually, you want to understand the environment quality factors inside the building environment. There's lots of things actually you need to consider. For instance, the temperatures, ventilation, that's what I just mentioned. We can use the simulations to evaluate them. There are also certain things like moisture, humidity, sound, noise, we can use simulation as well. And there's other things like related to spatial organization design and the digital twins, like the BIM building information model can certainly help us in that direction. I think that's the last slides I have. Then I'll stop and open floor for a question.
Thank you so much. Any questions? Yes, we can hear you. Xingyue, can you just speak up a little bit? It's not so clear.
Let me see whether can you hear me now?
Yeah, it's better.
Yes. Okay. So my question is, it's a wonderful presentation. For the you talked about both building environment and the built environment. Do you see any difference between the two?
I mean, most of the time we see built environment. We are actually talking about the environment actually is not natural. That's the environment like most of commercial buildings, the residential buildings, and there's the indoor space. You need to control the temperature, humidity, maybe even the fresh air circulation. So that's called a building environment because it's natural, right? It's not natural. And then when you're talking about the building environment, that's actually, you also actually extended that to the environment outside of the building boundary. So you have a surrounding environment, like you have in the urban environment, right? You have a, you're talking about the impact from labeling the buildings, and people also talking about those heat island impact effects. So those actually is the building environment because again, it's not within the building boundary. It's not the man-made, the building environment. Yeah, that's the difference between these two.
In your the last slide, you also mentioned the spatial organization. For that, certainly is my interest. Did you see any kind of design, the layout of the building, especially from three-dimension perspective, how it will impact the people's usage of the kind of indoor space?
Yeah, certainly, because again, the spatial organization, those layout will have significant impact on the well-being, occupant well-being. So again, if you have a very small office, you have a large office, you have all those kind of arrangement is going to have impact on people's productivity, right? So those things actually need to be studied. I think if you use this kind of the 3D tools can help people to visualize this, and then you certainly can help people to understand the importance for the space layout for the space, the organizations. Yeah.
Also, in your model, have you considered the different roles, capacities of individuals for people with disabilities, like kids, adults? Certainly, they will have different ways of interact.
No, for our current simulation, we only actually consider in that simulation suite I just presented. We only consider actually how many people in the room, and then but when we design the ventilation rate, that's actually we consider whether that is the office room or that is the conference room or that is the classroom, because based on the usage of these rooms, the required ventilation rate will be different. So that's like actually has the kind of the standard for those ventilation rate. Again, like even actually in the classroom, if it's just for elementary classroom, the value is different with the college classroom. So again, because this is depend on the occupant, yeah. But in our simulation, we did not at this time directly consider the interactions between the occupant and the HVAC system. See, for some, so right now people actually are studying like you actually can turn on off the thermostat. So they're trying to model occupant behavior, and then they incorporate this behavior into the modeling framework. But our study currently only actually consider those the occupancy information. So there's a difference between the occupancy and occupant.
Okay, so one last
go ahead.
Question.
Sure.
Yeah, one last question is did you in your model do you consider the alternative scenario? For example, since the purpose is for more energy saving and increase well-being. So in your model, when you putting them both together, you will allow the users, and let's say we change some thing inside or changes the configuration to see what's the output. Will you allow such operation?
As I mentioned, so it will be, but currently we did not actually model that. But in order to model that, you could actually incorporate some of the occupant behavior modeling, like agent-based model or some things, incorporating that, and then and then you run a simulation. So it could be done, but for our purpose, we really actually is trying to see those sensing technologies impact on the energy savings. So it's really, you have presence sensor, you also have the people counting sensor. So that's the hardware we have. So we only actually interface with the hardware to get information from hardware and help us understand occupancy in the building, and then understand what kind of advanced control we can deploy using those advanced sensing technologies.